Okay, in this example, we're going to look at a sort of an application or a real life example where we add vectors. So the question says we have a boat which travels across a river with a heading perpendicular to the river bank at a speed of 15 kilometers per hour. There's a downstream current of 5 kilometers per hour. Determine the resultant velocity of the boat. So anytime you get a question like this, a good idea would be to just draw the situation. So we've got a river, kind of like that. Now we have the boat, which heads out in a heading, which is perpendicular. So the boat's going to be going in this direction, perpendicular to the riverbank. So that's a right angle right there. There is a current which goes downstream, which I don't know which way is downstream, but I'll choose to draw it this way. And the current is at 5 kilometers per hour. So notice these two vectors, right? This is the velocity of the boat and this is the velocity of the current, will be perpendicular to each other. The resultant velocity, which is going to be sort of the actual result of where the boat would go, will be the sum of these two vectors. And notice they're placed head to tail. So the sum would be this vector here. Okay, and this should make sense, right? If you head out perpendicular to the riverbank, but the current is pushing you downriver, then you're going to end up down here a little bit. So we want to figure out what's the sort of actual velocity of the boat. So we need to introduce some variables here. I'm going to say let b equal the velocity of the boat in still water. So what we mean by the velocity of the boat in still water is if there was no current, sort of how would that boat be going? And that's kind of this velocity here, where it headed. So this is the velocity or the vector b. This one here, the current, I'm going to let be c. So c, which is a vector, will be the velocity of the current. And r will be the resultant velocity, which is kind of the actual velocity of the boat. So that term resultant velocity is often the word we use for the sum of two other velocities. So in this example, we need to figure out sort of this third side in the triangle. And the good thing about this one is because this was a right angle, this right here is a right angle. So the way you're going to figure this out, because it's a right angle, is just using Pythagorean theorem. You don't need to use the cosine law as we did in previous questions. So we know that the hypotenuse squared, which in this case would be the magnitude of r squared, will be equal to the one side, which is the magnitude of b squared, plus the magnitude of c squared. Make sure you've got the magnitude symbols when you write this. If you just said r squared, if you just had like this, that's wrong. This doesn't mean anything. You can't square a vector. Remember that a vector includes direction. We're just talking about the magnitudes here. So from the question, the magnitude of b, so that was the speed of the boat, was 15. So that would be 15 squared plus the current speed, which is 5 squared. So that's the magnitude of r squared. So the magnitude of r will be equal to the square root of, so 15 squared is 225 plus 5 squared is 25 equals the square root of 240, which is approximately equal to, oh, did I say 240? Of course not 240, 250. 250, which I'm going to get a decimal here. So I'm not just going to simplify the radical. I'm going to get a decimal approximation, and that's because anytime you're looking for like a physical quantity like velocity, if it was a distance, um, it, you want to give it in a decimal, or you don't want to say it's square root of something kilometers per hour, right? You want to give it like an actual number to get a better sense of what that is. So the actual speed of the boat would be 15 kilometers per hour. Now, we were asked for velocity, right? Determine the resultant velocity. Velocity is a vector. So that means we need to do two things. We need to figure out its magnitude, which is this. So that's the magnitude. But we also need to figure out the direction. So the direction is going to be, like we're going to have to get an angle. So probably the easiest angle would be this angle right here. So the way you would get that is just using a basic trig ratio. Tan theta is equal to the opposite side, which is the magnitude of C, over the adjacent side, which is the magnitude of B. So that tells me that tan theta would be equal to magnitude of C was 5 over magnitude of 15. So theta equals the inverse tan of 5 over 15, which reduces to 1 over 3, which is approximately 18.4 degrees. Okay, so we know that the angle here is 18.4 degrees. That doesn't really give me the direction, right? I can't say the direction is 18.4 degrees. You got to have some type of reference here. And now I want to caution you here. The biggest mistake I'll see when students do this question is they'll say, okay, well, that's 18.4 degrees east of north. There is no cardinal directions in this question. Nowhere in the question does it say north is this way and south is this way, right? There's no reference to north, east, south, west. Just because on your paper you drew the river going this way doesn't mean the river goes east, west, right? North doesn't always mean up on your page. So you need a way to kind of reference it. And go back to the question, and how did they reference their direction of the boat? They said perpendicular to the riverbank, so they gave the angle here that the direction made with the riverbank. So we'll do the same thing. We want to give this angle here. So here's the resultant. So we're going to give the angle that the resultant makes with the riverbank. We figured out this angle in here to be 18.4. So this angle, I'll call it alpha, is going to be 90 minus that. So alpha equals 90 degrees minus 18.4 degrees, which would be equal to 71.6 degrees. So we could say the direction is 71.6 degrees from the riverbank downstream. Okay, so therefore the resultant velocity is 15.8 kilometers per hour. So that's your magnitude in a direction of 71.6 degrees from the riverbank downstream, headed downstream.